So let's have this example for the elongation of a spring. So determine the elongation of a helical spring composed of 20 turns of 20 mm diameter wire on a mean radius of 90 mm when the spring is supporting a load of 1.5 kilonewtons and the modulus of rigidity is equal to 83 gigapascals. So we have, the load carried is equal to 1.5 kilonewtons. The mean radius of the coil is equal to 90 millimeters. The diameter of the wire of the spring is 20 mm. So we have also a given the modulus of rigidity is equal to 83 gigapascals. So how do we compute for the deformation of a spring? That's equal to, we have 64 times the load, the radius raised to 3, the number of turns, this is divided by the modulus of rigidity, the diameter raised to 4. So all we have to do, I think, is more of a direct substitution. So we have now delta is equal to, this is 64 multiplied by, the load is 1.5 kilonewtons, let's say this is 1,500 newtons. So multiplied by the radius, we have 90 millimeters, this is raised to 3. Then the number of turns, according to the problem, we have the number of turns equal to 20. We have 20 turns. This is divided by the modulus of rigidity. Let's have it in megapascal. So this is 83,000 megapascals or newtons per square millimeters. Then we have the wire diameter is 20 millimeters. This is raised to 4. So we'll be having the delta. If we are to do unit analysis, cancel newtons, mm to the fourth, this is mm squared, so we'll be having mm squared. Then this is mm cubed, so cancel mm cubed, so will be 1 degree or 1 degree for mm, that will be the remaining unit. Since this is deformation, it should be expressed in terms of millimeters. So let's compute, this is 64 times 1,500 multiplied by 90 raised to 3 multiplied by 20 turns divided by 83,000 megapascals divided by 20 raised to 4. So we have the deformation is equal to 105.398 millimeters. 105.398 mm. So nearest value in our choices is 105.4 mm. So that will be our answer. So let's have an example for torsion. So a hollow steel shaft with outer and inner diameter of 10 centimeters and 5 centimeters respectively with an applied torque of 12,000 Newton meter. So what is the maximum shearing stress? So we are looking for shearing stress due to torsion. So we have again, this is the shearing stress is equal to the applied torque multiplied by the radius. This is divided by the polar moment of inertia. If we have a hollow section, what will be our radius? Is it the radius of the empty space of the hollow shaft or the radius of the radius or our outer radius? So our radius will be, this is the radius of the outer section, that is the 10 centimeters. So we have 10 divided by 2. We have a radius of 5 centimeters or the same as 50 millimeters. So we have the torque, and again, how to compute for the polar moment of inertia. This is pi times, supposedly, pi times the diameter raised to 4 divided by 32. But since it is a hollow section, we are to remove the empty space. Minus pi times the diameter raised to 4 divided by 32. So we have the shearing stress is the same as the applied torque. So our radius is, that is the larger diameter divided by 2. This is divided by, we may factor out the pi over 32 is multiplied by the outer diameter raised to 4 minus the inner diameter raised to 4. So let us now substitute. We have the torque is equal to 12,000 Newton a meter. So we are multiplying 1,000 millimeters to 1 meter, since our unit on our choices is megapascals. I multiplied by the diameter over 2, that will be the outer radius. We have 50 mm. I divided by our polar moment of inertia, that is pi divided by 32. Our outer diameter is 10 centimeters, or that is the same as 100 millimeters. So 100 mm, this is raised to 4, minus our inner diameter, that is 50 millimeters, and this is raised to 4. So let's compute for the value of the shearing stress. So this is the same as 12,000. I multiplied by 1,000 to be in Newton mm. I multiplied by our outer radius, that is 50 millimeters. So that is divided by pi over 32. Our outer diameter is 10 centimeters or 100 millimeters. That is raised to 4 minus our empty space, the 50 mm diameter. So we have that shearing stress is equal to, we have now 65.19 megapascals. So if we are to do unit analysis, mm to the 4th, this is mm squared. So the remaining unit will be the same as Newton per mm squared, or the megapascal. So we have 65.2 megapascals. So the nearest value is letter B. And next in our discussion, we have the shear end moment. So, two uniform loads, 112 kilonewtons per meter acting downward are supported by a uniform upward pressure, omega, as shown in the figure. So, which of the following most nearly gives the maximum moment? So, if we are to recall some of the concept for shear end moment, so we have the slope of the shear diagram is basically equal to the magnitude of the load. Then we have slope of the moment diagram is basically equal to the magnitude of the shear. Okay. So other than that, since we are looking for the maximum moment, the magnitude of the maximum moment, at the point wherein shear is equal to 0, possible that at that point we have the maximum moment. So we are to locate we are to locate points of zero shear, and if we have several points, those are candidates for the location of the maximum moment. So let us first determine the upward uniform load. So this problem is one of our actual board exam. So how do we determine the uniform load? That is by summation of forces, vertical, upward forces to be 0. So we have the uniform load. This is modified by the total span. That is 1.5 plus 2. That is 4.5. 6 plus 1 we have. That is 7 minus the two uniform downward loads. 2 times 112. What is the span per uniform load? We have 1.5 equal to 0. So let's determine this upward uniform load. That is 2 times 112 multiplied by 1.5. So this is divided by 7. We have that value equal to 48 kilonewtons per meter, since there is also uniform upward pressure. So since we have now this value equal to 48 kilonewtons per meter, we may simplify our uniform load. We may do the summation already for this spans, just to simplify our uniform load. So what is the equivalent of 112 112 minus 48. 112 minus 48 is equal to 64. So we may rewrite this loadings as 64 kilonewtons per meter. So since we already subtracted 48, we remove that loading for this span of 1.5 for both uniform loads. So we subtract 48 just to simplify our load diagram for an easier way to draw our shear diagram. But for our shear diagram, for the shear diagram, so let's start on this one. The rest, we have this is the same as 48. What is 48 times 1? That is upward, so this is a positive line. This is 48 times 1 is equal to 48. And the magnitude of the shear at this point is equal to 48. So by the way, if we have our load diagram is, what is the degree of our load diagram? Uniformly distributed load. That is a 0 degree. Therefore, our shear diagram will be first degree and our moment diagram will be at a second degree. So we increase the degree of the graph as we go down. So this is a first degree straight line. So we have 48 minus 64 times 1.5, that is downward. So 48. We have 48 minus 64 multiplied by the span 1.5. Right, we have that shear equal to, this is negative 48. We have negative 48 plus, again, upward load. 48, this is also 48 kilonewton meter. Negative 48 plus 48 times 2. That is equal to positive 48. So I think we are just repeating values. So 48 minus 64 times 1.5 is again, we have again this is negative 48. Then negative 48 times negative 48 plus 48 times 1, that is equal to 0. So this is our shear diagram. I can still recall on our actual board exam, one of the required is what is the maximum shear, and our maximum shear is obviously 48 kilonewtons. That is our maximum shear. So now since we are just looking for the maximum moment possible, look for the points of zero shear. But for this case, we have 3 points. So these are candidates for the location of the maximum moments. Okay, so but first, you may determine this, you may use area method to determine the magnitude of the moment. Okay, so possible that the area of this shear diagram is the maximum moment. So if you are to do ratio and proportion, 48 and negative 48, this is a span of 1.5. So more likely this is 0.75 meter, 0.75 meter. So how do we compute the moments? So let us designate some name of points. So let's say this is at point A, or we may have it here. So let's say this is at point A. What is the magnitude of the moment at A if we are to use the area method? So moment at A is obviously area of a triangle, 1/2 of 1 meter. This is 1 meter for a magnitude of 48. So this is obviously equal to 24 kilonewton meter. That will be the moment at A. So how do we draw, or what will be the opening of the curve? What will be the opening of the curve? So as you can see, this is from Okay, from zero shear to positive shear. So a while ago, we said that the slope of the moment diagram is equal to the magnitude of the slope of the moment diagram is equal to the magnitude of the shear. So from zero shear, what is the appearance of a line having a slope equal to zero? That is horizontal, zero shear. So that is a horizontal line. If we say the slope is equal to zero, then positive 48, that will be upward to the right for a positive shear. So therefore, what will be the appearance of the graph or the moment diagram? That is a curve that opens upward. So from zero shear to positive shear. So we have that value equal to, or we have that moment equal to 24 kilonewton meter. A curve that opens upward. This is 24. So let's say this is at point B. That is the first point of the moment equal to 0. What will be the moment at B? So starting at A, what is the moment at A? We have 24 plus 1 half. What is the base? We have 0.75. What is the height? The height is equal to 48. So we have the moment at B is now equal to, we have the 24 plus 0.5 of 0.75 by 48. So we have that as 42 kilonewton meter. Possible that this is our maximum moment for a reason it is that its location is a point of zero shear. What will be the opening of that curve? If you are to observe from positive 48 to zero shear, how do you write that? So from a positive slope, this is because of a positive shear, then a zero shear. So the curve should opens downward. So this will be a curve that opens downward. And the magnitude is equal to 42. This is the 42 kilonewton meter. So is it one of our choices, the 42 kilonewton meter? So that is equal to 42 kilonewton meter, letter D. That will be our possible maximum moment. So let us just consider this one. What will be the moment on this point? That is the same as 42. Let us just compute that. 42 minus 1 half of 0.75 times, since it is negative, 48. We have that again as positive 24. Then this is 48, negative 48. This is obviously 1 meter. So since that is negative, obviously minus 1 half of 48 by 1 meter. That will give us a moment equal to 0. So which means our answer for the maximum moment is the 42 kilonewton meter. This is the maximum moment of the moment on our diagram, M max. If we are just to complete, but in our board exam, you don't need to complete the diagrams as long as we have the answer. So we have, this is again, as you can see, we are starting at the same values. So 48, then negative 48, then 0. So this diagram will be just repeated on the next part of the moment diagram. So this is 48 times 1 meter over 2 is positive 24. Positive 24 plus, again this is 0.75. We'll be having again the value of positive 42. This is again 42 kilonewton meter, then 42 again minus. So we will go back with the value of positive 24. 24, okay, minus 1 half of 48 times 1, that is negative 24, that will give us 0. This is the complete moment diagram. But again, in our actual board exam, if you are able to determine the correct answer, no need to complete the diagram. So our answer is 42 kilonewton on meter. Again, that is letter D. Let's discuss beam stresses. We have the first one, the flexural or the bending stress. So for example, we have this beam. If it is bending downward, this means it is acted by a positive. This is caused by a positive moment. So for example, this is the line of the neutral axis for a positive bending moment. Above the neutral axis is obviously under compression, and below the neutral axis, this is under tension. So how to compute for the bending stress? That is equal to our general equation for bending stress. That is the moment, we have the value of C divided by the moment of inertia. So we're in, for example, if we have a rectangular section, okay, so for example, this is the line of the neutral axis. So the value of C is the distance. That is the distance from the neutral axis to the extreme fiber of the beam. So this is for any section, since this is the general equation. So since we have our beams are mostly rectangular, so for rectangular section, so we have the bending stress can be computed as 6 times the maximum moment divided by the base times the depth strain. So this is only for a rectangular section. So this is for flexural or bending stress. Okay, then we have the horizontal shearing stress. So in some references, that is the same as f sub h. In other references, that is the same as the f sub b. So again, for a given section, for example, a rectangle, so if this is the neutral axis, that is the same as the stress between fibers. So for example, since the fibers above the neutral axis is under compression, and the fibers below the neutral axis is under tension. So that's the stress, lateral stress between fibers of the given beam. So for the general equation, or for any section, that is the applied shear. Okay, we have the statical moment area divided by the moment of inertia times the width. This is for any section. So for rectangular section, so we have the shearing stress is equal to, this is 3 times the shear divided by twice the area. This is the shearing stress at the neutral axis. Okay, so these are the most common type of beam stresses. We have the flexural or bending stress, the horizontal shearing stress. Let's have an example. So let's have this example. So a simply supported beam, 120 millimeters wide, 180 millimeters deep, which is 6 meters long, carries a uniformly distributed load of 4 kilonewtons per meter. Compute the maximum shearing stress developed in the beam. So we have the maximum shearing stress is the same as the shearing stress at the neutral axis. Okay, this is for a rectangular beam. So how do we determine the shearing stress? That is the same as 3 times the shear divided by twice the area. Since we are looking for the maximum shear, we should determine the maximum. Since we are looking for the maximum shearing stress, we should use the maximum shear. So for a beam, at what point can we find the maximum shear. So if we are to determine the support reaction, since this is a simply supported beam, uniformly distributed, 6 times 4 is 24, divided by 2, support reactions will be 12 kilonewtons. And take note, for simply supported beam, okay, the maximum shear will be always on the support. So this will be 12 kilonewtons, the support reaction, that is our maximum shear for simply supported beam. So maximum shear always occurs on supports. So if you have to do the shear diagram, obviously, our maximum shear on our diagram will be 12 kilonewtons. So computing for that value, we have the maximum shear is equal to 3 times the maximum shear stress is equal to 3 times the maximum shear divided by twice the area of the beam. Again, so that is at the neutral axis. Neutral axis at support. Okay? So we have now the maximum shear stress is now equal to 3 times. What is our maximum shear? We have that as 12 kilonewtons or 12,000 newtons. This is divided by twice the area of the beam, that is 120 mm, multiplied by 180 mm. Alright, so we have the maximum shearing stress for this beam is equal to, it is the same as 3 times 12,000 divided by twice of 120 by 180. So we have that as 0.833. As you can see, Newton mm. This is the same as newtons per millimeter squared. Okay, this is the same as megapascals. So if you are to multiply it by 1,000, so this conversion multiplied by 1,000 kilopascals is to 1 MPa. And we have that as 833.333 kilopascals. So that will be our answer. So 833.333 kilopascals. So our answer will be letter C. Okay, so what about if we are required to determine, for example, the maximum for example, we are required to determine the maximum bending stress. So obviously, we need the maximum moment. So if we don't have a formula, you can do the shear moment diagram. So this is the same as 12 times, this is the same as 3 meters. 12 times 3 is 36. Triangle divided by 2, that is 18. So from positive slope to zero slope, so it will be a curve that opens downward. So 3 times 12 is 36 divided by 2 is 18. So our maximum moment, Mmax, is equal to 18 kilonewton meter. But since this is a uniform loading, my Mmax can be computed as the uniform load, the length squared divided by 8. It's the same as 4 times 6 squared divided by 8. So we have, that is the same as 6 squared is 36 divided by 2, since 4 over 8 is 1/2. That is the same as 18 kilonewton meter. So how to compute for the maximum bending stress? That is F sub B maximum. For this loading and this section, that is, since rectangular, 6 times the moment BD squared. So we have that as 6 times, we have 18 kilonewton meter. This is multiplied by 1,000 newtons is to 1 kilonewton. I multiplied by 1,000 millimeters is to 1 meter. Okay, divided by the base width of the beam, we have 120 millimeters. The depth of the beam is equal to 180 millimeters. This is raised to 2. So this will be the maximum bending stress of the beam, and it will occur at the mid span. So let us compute. We have the 6 times 18 multiplied by 1000 squared to be in Newton mm. I divide by 120, divided by 180 squared. So we have that as 27 is equal to 27.778. So the remaining units will be in terms of newtons per millimeter squared, or the megapascals. This is our maximum bending stress. So let's have an example for a regular beam. So a beam has a T-section built up by 2 plates as follows. So we have 200 mm by 40 plate as the flange. So this is the flange. Then we have 100. This is 100 millimeter by 20 mm. This is the web. So the maximum shear force acting on the beam is equal to 60 kilonewtons. So first, number 11. Which of the following most nearly gives the shear stress at the neutral axis? First, we need to locate the neutral axis, then compute for the moment of inertia. So first is by, let us assume a distance from the top of the beam. Let's say this is bar y. So we have area total multiplied by bar y is equal to the summation of area times y. What is our total area? Our total area is equal to 200. Let us compute for the total area. So area total is 200 by 40 plus 100 by 20. So we have a total area of 10,000. This is 10,000 square millimeters. Alright, so we have, this is 10,000 multiplied by the bar y is equal to, let's say the flange will be area 1 and the web will be area number 2. So that is area 1. What is area 1? This is 200 multiplied by 40. What is its distance? The distance of its centroid. Let's say our reference line will be on the top of the beam. This is our reference. So this is the distance for y for area 1. So it is the same as 20 plus area 2 is 100 millimeters by 20 mm. What is the distance of its centroid towards the neutral axis, towards our reference? That is 40 plus 50. So the distance is, it says 90, this is 20. So we divide by 90. So what is the location of the neutral axis from the top of the beam? So we have 200 by 40, this is divided by 20, okay, plus 100 by 20 times 90. This is divided by 10,000. So we have 34 mm. Or we have 34 millimeters. So it means, as you can see, what is the thickness of our flange? That is 40 mm. So it only means that the location of the neutral axis is within the flange. Okay? So this is the location of neutral axis. Y bar is equal to 34 millimeters. Okay, and this is our neutral axis. So since we have now the neutral axis, let us compute for the moment of inertia with respect to the neutral axis. This is the same as the centroidal moment of inertia, or the summation. This is the summation of the centroidal moment of inertia plus the area times y squared, or distance, let's say distance screen. So how far is the centroid of each area from the neutral axis? Okay, so we have that as, okay, the first one, area 1, our base is 200, the depth is 40, this is cube divided by 12, plus the area, 200 by 40, plus how far is the centroid of area 1 from the neutral axis? If this is 34, this is 20. So that is the same as 34 minus 20 squared. Okay, plus we have area number 2. Area number 2 is your base is 20, your depth is 100. This is 100 cubed divided by 12 plus the area. We have 100 multiplied by 20. It's a centroid. So I will do its centroid is 90 from the top of the beam. So this is 90. So which means the distance of its centroid towards the neutral axis is 90 minus 34 squared. So this will be our centroidal, or no, the moment of inertia with respect to the neutral axis. So we have that as okay, 10.573. This is times 10 raised to 6 millimeters to the fourth. Okay, so that is our moment of inertia with respect to the neutral axis. So what is our first question? Okay, our first question is, which of the following most nearly gives the shear stress of the neutral axis? So if we are just to consider the flange, since that is the location of the neutral axis, okay, so this is 34 millimeters from the top of the beam. Okay, we can just use the area above. So I'm using area above. Okay, so what will be our statical moment of area? The statical moment of area is the area above the neutral axis. Actually, we may also use the area below, but it is more complicated. The area above is more simple. So we choose that a simple area. So that is the same as, what is the area above? That is 200 times 34, and it's a centroid. Again, this is at a distance of 14 mm. That is the 34 mm minus 20. So multiplied by 14. Sorry. It's not, we're not using 14. That is the area above. The centroid of this area is at a distance of 17. We are not using the 14 mm. That is the centroid of the area above the neutral axis. That is half of 34. We are using 17. Any correction on that? We have this 200 multiplied by 34 times 70. We have that as 115,000. 600 millimeters raised to 3. So we have the shearing stress at the neutral axis is equal to the maximum shear, the statical moment of area divided by the moment of inertia should be with respect to the neutral axis times the width of the section. What is our width? What is the width of the neutral axis? That is the same as the 200. So a while ago, the given shear is 60 kilonewtons or 60,000 newtons. This is multiplied by Q, 115,600 millimeters raised to 3. This is divided by, we have this one, we have 10.573 times 10 raised to 6. This is millimeters raised to 4. What is the width of the section wherein we are computing for the shearing stress? 200 mm. If you are to do unit analysis, obviously the remaining unit will be in terms of newtons per mm squared or the megapascals. And let's compute for that value. So the maximum shear is given as 60 kilonewtons or 60,000 newtons. Multiplied by 115,600. That is the area, statical moment of area above the neutral axis. Over 10.573 times 10 raised to 6. That is the moment of inertia with respect to the neutral axis. And multiplied by the width of the neutral axis is 200 mm. So we have that as 3.28 megapascals. So in our choices, we have 3.28 megapascals. We have letter, that's letter B. The other question, or the follow-up question of the problem is, which of the following most nearly gives the shear stress on the web at the junction of the web and the flange? So we are looking for the stress on the web at the junction of the web and the flange. So at this point, all we have to do is compute for the value of the new statical moment of area. So again, if this is the section under consideration, you may consider area above or area below this line. I'll be using this area below this time. So, and it's a distance from the neutral axis. So what will be the distance? Okay, the distance is the same as 50. Since this is 34, we have a remaining 6 here. So this is 56 mm. So the statical moment of area is area 100 by 20 moment. What is the lever arm? That is the 56. That's why it's called as statical moment of area. You have to moment the area. So area times the lever arm. So that is 100 by 20 by 100 by 20 multiplied by 56. So we have that as 112,000 millimeters raised to 3. So, what is our width this time? What is the width of the section wherein we are computing for the shearing stress? What is the width of this section? The width is 20 mm. So this time, we have B is equal to 20 millimeters. So you have the shearing stress at the junction, let's say the junction on the web part. Since which of the following most nearly gives the shear stress on the web? Take note, we are to use the web, the width of the web, 20 millimeters. That is the shear statical moment of area divided by the moment of inertia with respect to the neutral axis times the width. So given on this problem, 60 kilonewtons shear, that is equal to 60,000 newtons. Multiplied by the statical moment of area of 112,000. This is divided by our computed moment of inertia, 10.573 times 10 raised to 6. Multiplied by the width, we have 20 millimeters. So this will be the shearing stress at the junction of the web. So we have 60,000, multiplied by 112,000. Divided by 10.573 times 10 raised to 6 multiplied by 20. So we have that as 31.78 megapascals. 31.78 megapascals on our choices, that is letter C. So let's have this example. This is an example of a combined stress. So also a passboard exam problem. So a hollow pole weighing 150 newtons per meter. That is the self weight of the pole. 3 meters high, 6 millimeters thick, with an outside diameter of 300 millimeters. So 300 millimeters minus the thickness on each side, we have 200 millimeters as the inner diameter. So the pole is fixed at the base, and it is subjected to a compressive force of 3 kilonewtons at an eccentricity of 100 millimeters. That is the distance of the point of action from the centroid of the pole. So acting at 100 millimeters from its centroid, and a lateral force of 0.45. Lateral, it is acting perpendicular to the pole. Acting horizontally, 0.45 applied at the top. So compute the maximum tensile stress. So this is a case of a combined stress. So this is the axial plus bending. So you have the total stress is axial, positive or negative force over area. Then for bending, that is plus or minus MC over I. The bending stress and the axial stress. So basically, we are using negative sign if it is under compression, and positive if it is under tension. So compressive stress, negative, tensile stress is positive. Take note that we are looking for the maximum tensile stress at the base. So let us consider the forces and what are their effect on the pole. What is the effect of the 3 kilonewtons and the self-weight? They are compressing the pole. So this means the 3 kilonewtons and the self-weight will give a negative axial force. So let us first determine the value. We have P, that is the 3 kilonewtons, plus 150 newtons per meter. So all we have to do is multiply it to its height. So this is multiplied by 3 meters. That will give us newtons divided by 1,000 to be in kilonewtons. So we have that value of the axial force. Okay, we have that as 3 plus 3 times 150 over 1,000. Okay, the value is equal to 3.45 kilonewtons. So this, the self-weight and the 3 kilonewtons will give a normal effect, a compressive effect on the column. Then we have, since it is an eccentrical load, it will cause a moment. So let's say this is a moment number 1. The same with the lateral load, it will give a moment. This is moment number 2. So let us compute for the moment at the base. This is the moment total. So summation moment at the base. And we have the summation of moment at the base is equal to 0. That is the moment total at the base is equal to the 3 kilonewtons multiplied by its eccentricity, 100 mm, that is the same as 0.1 meter, plus the lateral load, 0.45 multiplied by the height, that is 3 meters. This is the total moment at the base. So total moment at the base, that is 3 times 0.1 plus 3 times 0.45. So we have that as 1.65 kilonewton meter. So since, again, what is the effect of these forces? They will compress the column. So we have the total stress, which means if they are compressing the column, this is a negative axial stress. So since we are computing for the maximum tensile stress, we have to consider the positive bending stress to have a positive value. So plus the MC divided by the moment of inertia. If we are to imagine what is the deformed appearance of the beam, of the column, so it is like this. So the force will compress the column, the same with its self-weight, the 150 newtons per meter. But this moment, I will bend this portion. So it means this side is under tension, while this side is under compression. Basically, we are computing for the tensile stress at this portion. Okay, so let us just substitute. We have the total stress is negative 3.45 kilonewton meter or 3,450 newtons. Area, okay, so again, since it is a hollow, that is the outer circular area minus the empty space. That is pi over 4. Okay, outer diameter is 300 squared minus 288 squared. That is for the axial stress, okay, negative since compression. Plus the positive bending stress, that is the stress caused by these two on this portion. They are bending it to the right, so they are stretching this point. So plus what is the moment? 1.65. This is kilonewton meter. We are multiplying 10 raised to 6 to be in Newton mm. Multiplied by C. What is C? We are using MC over I since it is not a rectangular section. C is the distance from the neutral axis to the extreme fiber. So basically C is the radius of the circular pole. That is the outer radius, we have 150 millimeters. Okay, that is 150, half of the 300. Divided by moment of inertia. What is the moment of inertia of the circular section? I is equal to pi, the diameter raised to 4 divided by 64. That is the moment of inertia of a circular section. But again, that will be outer minus the empty space. So that is pi divided by 64. That is outer diameter 300 raised to 4 minus inner 288 raised to 4. So this will be the total maximum tensile stress, and supposedly since it is tensile stress, it should be positive. We have negative 3,450 over pi over 4. Outer area is 300 squared minus inner 288. Okay, plus 1.65. We're considering the positive bending stress to have tensile stress. Is 10 raised to 6 since we are to convert it to Newton mm. Divided by the C over moment of inertia, pi over 64 for a circular section. Is outer raised to 4, 300, inner is 288 raised to 4. So you have that value, and obviously since it is positive, it is tension. Positive 3.509 megapascals. Let's check on our choices. 3.509. Okay. Nearest value is 3.51 megapascals.